Hello viewers, welcome to my channel. In today's lecture video, I'll be talking about computer codes. I'm starting with four very simple codes like ASCII code, BCD, run length encoding and Huffman code. They are very simple but at the same time very much useful in a modern computer. I hope this basic knowledge will generate interest in you to know more about the more complex codes used for image compression, JPEG image, MPEG image, and for cryptography. If you are a college student or a inquisitive learner, this lecture video will be very much useful to you. So please stay till the end of the video and please don't forget to like, share and subscribe my channel. So let's dive in. First, we are going to see few definition. What is a code? It is a set of rules that will transform or convert some information in original form into another format. And why it will be converting? Because maybe we'll get some advantage in saving the storage space that will be required or for transmitting that data in the original format, maybe taking too much of bandwidth. But if you convert it in a coded form, it will save the bandwidth. So that is the definition of a code. It is just transforming the original information into another format. Now, binary code. In the binary code, the code word will have a string of zeros and ones, and that is called binary code. And there are few codes which are fixed length, where the code word will be of same length. Suppose you are converting alphabets, English language alphabet A, B, C, D. So A will also get the same length code, B will also get the same length code. If it is true for all other alphabets, then it will be called fixed length code. Some codes are not fixed length, variable length codes are also there. And we are going to take one example in Huffman coding, and where some alphabet will be represented with a smaller string, some will be represented with a longer string, depending on how frequently they appear. And the code length is the number of bits that is used in a code word. If it is a fixed length code length for all the codes are same. And if it is a variable length code, then we take the average code length. So in a binary code, the code word is a string of zeros and ones. And if we use n bits, we can represent at most 2 to the power n distinct information with it. And this n can be any number, but in choosing n, we should keep in mind that the code word should be optimized so that we get the benefit, right? We are transforming the original information into a different format. So we should get the benefit of saving memory space and transmission bandwidth. So code length should be accordingly. And also note one thing, these binary codes, they do not have mathematical representation. They do not mean mathematics, right? They are just a string of zeros and ones. And in most of the cases, it is true. But in one code, we are going to see binary coded decimal. It still has the numeric property. The bits have weight associated and it has a value. So it can be both, but most of the time, these string of bits, they do not represent a mathematics or number, and you cannot do addition, subtraction with them. So the first code in our bucket list is the ASCII code. ASCII stands for American Standard Code for Information Exchange, and it was introduced in 1968. It is also called alphanumeric codes because it transforms alphabets and numbers both. It also transforms all the punctuation marks that are used in English language into some code word, binary code, and it can be The original information can be visible or invisible character, and it will be transformed. Like I have just mentioned some of them: space, null, um, carriage return, line feed, etc. So it was introduced in 1968 to process textual data. The text files, so far we have seen number representation, decimal numbers were converted into binary, but how about the text? And this computer was invented in America, so the first need was converting the English text into some binary string so that they can be processed. And this first code is called ASCII code, and they used 7-bit ASCII code. And with 7-bit, 2 to the power 7, 128 code words could be generated, and that was enough for transforming all the alphabets: A, B, C, D, uppercase, lowercase, and the digits 0 to 9, then all the punctuation marks, and all the other things like the bell or the carriage return or the line feed. Everything was converted with 128 code word. And I'm giving you an example of the ASCII code, so that hello can be represented in a computer system. So the code, ASCII code for age with 7 bits was 11010000. They were just assigned. I'm going to show you the lookup table for the ASCII code. So E was this, and hexadecimal, this one is 68, because this upper 3 bits is 1106, and then 1000, this is 8. Then E is 65, L is 6C, 6C, and 6F. Okay, and the number 0 also has a ASCII representation, but right now it is not the number 0, it is the character 0, and it is 30 in hex, and 9 is 39 in hex. And all other punctuation marks and invisible characters like space, null, carriage return, line fit, etc., all have some representation in the ASCII code. And another thing is that in a byte, the byte is 8 bits long, right? So ASCII code was 7 bits, and the 8th bit was used as a parity bit. And this parity can be even or odd, anything, but I'm giving an example of even parity. So that 7 plus 1 is 8 bits. 8 bits together is called 1 byte. So usually in a computer, the unit of length of data is either a byte or a word, etc. So with 8 bits, you can also add the parity bit, and this parity bit checks if data is transferred from one place to another place. Then it is checking that there are 3 ones here, no? And to make it even, their even parity will be 1 here. But for the next letter E, there are already 4 ones are there. Even parity bit will be 0. And like this, it is used. So we can say ASCII code is also 8 bits, where the 8 bit is for the even parity. So let's look at the ASCII codes table. It is called a lookup table. So as I said, with 7 bits, you can generate 2 to the power 7 words, code words. So all of them are listed here from 0 to 127. So total 128 code words are there. So 0, the first code word, is assigned to null. And then this 10, decimal 10 or hexadecimal A, has been assigned to line feed. Let's see the numbers. This 0, this 48 in decimal, 30 in hexadecimal, assigned to represent the 0 character. And then 57 is assigned to 9, and like that. Capital A is assigned to 41 in hex. Then small a is assigned to 97 or hexadecimal 61, and like that all 128 code words are gone that are used in modern computer for English language processing. Now the thing is that there are so many other languages in the world, and nowadays the computer can process all other languages like the Chinese language, Devanagari language, Bengali language. They have their own alphabets. So 7 bits of ASCII code was not enough to represent all of these languages. In the computer also we use emojis and many other symbols are there. They also need representation. So later on the length of the code word was increased, and that is called Unicode, which is universally accepted. And this Unicode has different forms, UTF-8, which is variable length. It takes 1 byte to 4 bytes. Like English language was the first language that was used in ASCII code. So to keep the compatibility in Unicode with 1 byte, this English language will be used. And for other languages like Bengali or Devanagari, more length bytes are needed. So if UTF-8 is used, then it is a variable length code. It will take 1 byte. Maybe it is 1 byte is given to the predominant English language because English was the first language the computer used. And for Bengali, it will give 4 bytes. So to store something in Bengali, it will take more memory and more bandwidth than that of English. And then in UTF F16 format is also there. Then UTF-32 format is also there. This UTF-32 format is fixed length 4 bytes. In this format, all the languages have the fixed size code word. So English also 4 bytes, other languages also 4 bytes. One disadvantage of this code is that it is just taking too much bytes. So those are the things that need to be taken, like when you measure the efficiency of a code, you see what is more efficient, UTF-8 or UTF-32. Now let's look at the second code, which is called binary coded decimal. In binary coded decimal, individual decimal digits are given a new code, which is a string of binary numbers. So 0 to 9 will have a code, and if it has, I told you before that it has some numerical values also. It is also called 8421 weighted code. And if you have a big number with many decimal digit, then all the digits will be individually converted to code word. And these BCD codes are used for numerical displays. You must have seen it in a hospital where the patients are called and they show that which number of patients are with the doctor right now. Like this, it is used for 7-segment display. And in this also addition and subtraction can be performed, but it is a little different from the other binary number addition and subtraction, and we are going to see that. So this is the BCD code. Here I am showing 0 to 9 decimal numbers, and their codes are 0000, because you know that to represent 9 binary number is 1001, to represent 8 it is 1000. So 4 bits are needed. So it is also an example of a fixed length code. And so BCD code is same as the binary number corresponding to 0 to 9. And but 10, 11, 12, 13, because they are 2 digits with 4 bits, you can have a binary representation, but those are not represented in the BCD code. Not used, not used, not used. So how are they represented? As I am saying that 10 is a decimal number with 2 digits, they will be individually given a binary code. So one example, 1024 is a decimal number. So You just convert them individually, 8421 BCD code. So 1 is 0001, 0 is 4 zeros, and 2 is 0010, and 4 is 01000. Okay, so to represent 1024, you need 16 bits. Let's do another example. 954 is a decimal number, and 9 is represented separately 1001, 5 is represented 0101, and 4 is represented separately as 0100. So the BCD for 954 is 1001, 0101, 0100. This is how you represent decimal numbers having multiple digits. And you can do addition and subtraction also. Let's do one addition with BCD code. So this is, suppose you have to add 75 with 35, one 7-segment display uh, where the 2 digits can be displayed is showing 75, another is showing 35. If you have to add them, then in decimal addition you get 110, but here you are seeing when you are adding them, you are getting 110, 101. But this one 1010, it doesn't have a BCD representation, right? Because it is the last one was number 9, that was 1001. So 1010 was not used. So you have to correct it. So to correct it, you add 6 to both the digits. Remember, because we are not utilizing 6 representation from 16 from 10 to 15, 6 representation we are not utilizing in BCD code. So to skip that, you are adding 6 to both the digits, and then you are getting this code with an extra carry. So right now, after this correction, you are getting the right number. And this is the rule for BCD addition. So what is the rule? Step 1, add the two BCD number using the rules for binary addition. And if a 4-bit sum is equal to or less than 9, it is a valid BCD number. And if a 4-bit sum is greater than 9, or if a carry out of the 4-bit group is generated, it is an invalid result. Add 6, which is 0110, to the 4-bit sum in order to skip the 6 invalid BCD code words and return the code to 8421. If a carry results when 6 is added, simply add the carry to the next 4-bit group. So here there was a carry was also generated. So this is one BCD code, and this the BCD code. Let's look at the BCD to 7-segment decoder, how it works, why it is needed. So BCD 4 bits long BCD codes are there from 00, and the last one is 1001. So when all zeros are coming here to the input to the decoder, here it should display 0. That means these are LED lights, okay, individual LED lights. There are 7 LED lights are there. But when it is all 0 in the input of the decoder, A should be lit, B should be lit, C, D, E, F. Only G shouldn't be lit. Here the input-output function table is given for the decoder. So all zeros, A is 1, A, B, C, D, E, F, all ones, only G not 1. Likewise, where it is 1 in the input side, only B and C should be 1. And it is all others are 0. And it is like that. When it is 9, then A, B, C, D, and after that E is not lit, but F is lit and G is lit. And BCD code is used for 7-segment display. Let's look at the third code, which is called run length encoding, or RLE. It's very simple, very easy code. So it was the first code that was developed, and it is used to compress the data. Suppose you are storing a lot of data, and if you can compress it with less code words, then you are saving memory or communication bandwidth. And suppose there the text is this, there are 17 A's are there, after that 7 B's are there, and 13 C's are there, so total 37 bytes as per ASCII code. I have added the 8th parity bit also to make it full. So there the requirement should be 37 bytes. But with length encoding, you are just counting how many A's are there, and you are writing it 17A and then 7B and 13C, so that you know that this 17 is a count and is not part of the text. You use some special character. I am depicting it with hyphen here. So here you are using total 8 bytes. Originally it was 37, now you are using only 8 bytes. So it is a lot of saving. In example 2, we write like this, excellent, and with so many exclamation mark. So here in RLE it will look like excellent, then 20 exclamation. And a big saving will come when you have a image like this. It's a 256 by 256 image that takes a lot of data to be stored, because these colors are represented with red, green, blue channel pixel values. But if you are doing run length encoding, you will just say that 128 by 128 white pixels are needed and 128 by 128 red pixels. So a lot of savings will come from run length encoding. The last coding algorithm that I am covering in this lecture is the Huffman encoding. It is a variable length encoding. So Huffman coding is a popular compression technique that assigns variable length codes to symbols so that the most frequently occurring symbols have the shortest code. And how you get those code, a binary tree is constructed progressively with the least frequent occurrences to most frequent occurrences of symbols. The branches are assigned 0 and 1 from top to the top of the tree to get the code word. I'm going to show you with example. And Huffman code is also called a prefix code. Here, no code word is a prefix of another code. So when you are converting it back from the code to the original information, there is no problem. I'm going to show you. And if that is the case, we call it a lossless compression technique or lossless encoding. On decoding, the symbols are reassigned their original fixed length code. It is a lossless coding technique, and coding efficiency of Huffman coding depends on the text. It's a dynamic encoding, right? Like the run length encoding, and this Huffman, it is dynamic. There is no lookup table, no dictionary where you find. You actually have to process the text and to find out its frequency or how many times it is appearing, and then you are getting the code word. Let's find out the code word with an example. So here my example is America, Africa, India. I have written all in capital letters here. So first of all, ASCII code, we are calculating what will be the, if we use ASCII code, then there are 22 letters are there, counting the commas and the spaces also. And if I use 7 bits ASCII code, it will take 22 into 7, 154 bits there. And we are going to see the advantage of Huffman coding. That's why I have calculated the ASCII code bits first. So in Huffman coding, you take each alphabet A, how many times it appeared. So A appeared 5 times. America has 2 A's, Africa has 2 A's, and India has 5. Then next is I. I is 1, 2, and 3 and 4 times. Okay, and I have computed it already and arranged them from highest frequency to lowest frequency. So you can check, verify with some other letter also. R, America has 1 R, Africa has 1 R, so total 2 R's are there. And space, how many space is there? Here one space, another space here. Comma is also 2. Let's see, D D is only in India. So after you calculate the frequency of the letters, you create a binary tree. And for creating binary tree, you start with the lowest frequency alphabets, and those will be your leaf nodes. And let's see how it happens. So M has 1 frequency, E has 1. So you combine, you are generating a binary tree. So if you have two children, you can have a parent, right? So M occurred 1 time, E occurred 1 time. So if you combine them to a parent node, so total frequency will be 1 plus 1, 2. You have many such 1 frequencies. So you do F and N 1, 1, you are getting another parent 2. Then you are getting another one was there, so you are combining it with a 2 and R and D, you are getting frequency 3, total frequency 3. And then you are getting C2 and comma 2, you are getting another frequency. Okay, and then after that you are combining C and space and this together, and you are getting a total frequency of 4. And here you are combining 2 and 3, you are getting a frequency of 5. 4 and 4, you are getting a frequency of 8. Now you will be combining 5 and 4, and you are getting 9. And here 5 and 8, you are getting 13. And 9 and 13, you are getting 22. So the root of the tree is 22. And these are the leaf nodes. This space is also a leaf node, A is also a leaf node, 4 is also a leaf node. So when the codes will be generated, you will be traveling from top till to the leaf node. So A will get a code, and it is a binary tree. To one branch you assign 0, to another branch you assign 1. And it is true for all the branches. To one branch you assign 0, another branch you assign 1. So no rules that left has to be 0 or right has to be 1, no such rule. So after doing that, uh, you are traveling from top to the leaf node. So to come to A, you are traveling this 0 and 1. So A should have a code of 0 and 1. And you see this code is very small, only 2 bits. And A occurred 5 times, that's why it was given a small length code. Whereas the code for F will be 1000, like that. Okay, you check for others also. So I'm now computing the Huffman code for A 01, Huffman code for I. Where is I? I is here, so it will be 110. It should be 110. Then for R is here, so it will be 1011, and like for all other letters. So now you can see the code words are of variable length. A was most frequently used, so it has got a small code word. And the code words, the letters which are used least frequently, they got big code words. So now my text was America, Africa, India. So it will look like this. And you can see no code word is a prefix to another. And I have actually distinguished each code with a hyphen. They will not be used Actually, they will not be used. But right now, to learn the code, how it works, I have given those hyphens, those are extra. And you can see the code for A is 01, and this 01 doesn't appear anywhere in the beginning. So for the 110 code, 110, nowhere 110 is there. So when you are converting this Huffman code to the original text, there won't be any problem. You get 01 and you know 01 is one of the code word, so it is A. And 0010, 00 is 00 is there, 00 is there, but this is not a complete code word, no. So there are three options for 00. You check another bit 1. 001 is also not there, uh, and then 0010. When you come to 0010, then you know that it is M. So conversion from this code to the original text is lossless. No information is lost there. Dear learners, today you have learned about some simple but very essential computer codes that are needed for the workings of a computer. First one was ASCII to represent English language. I have also briefly gone through Unicode, which can represent all other languages, but I haven't elaborately discussed that. Maybe some other video I will discuss it. And then the second code was BCD, binary coded decimal, that is used for 7-segment display, run length encoding, and Huffman code. And there are so many other codes are needed, required for a computer system. Next one I will be covering is a error detection and a correction code, or the Hamming code. Hope it is generating interest to you to learn about more codes that are needed in a computer system. If you have liked my this lecture video, please like, share and subscribe.